Hello everyone. So here's the next video. We've got some review questions I've left in the file for you that I'll just sort of scan through quick as part of the video. Main focus of the video is going to be uniform circular motion still, and analyzing things like the Gravitron ride at the fair, and a vertical uniform circular motion example, the loop-de-loop. So think of the little tracks for little cars that go and you'll see in the video, little loop-de-loop, right? It goes upside down through a loop. So let's get at it. So the review question is in here, usual stuff, right? Give you the mass and radius and how many revolutions it goes through and so on, right? And asking you some questions, right? So I went with my usual here of circumference information to get the speed, and then the speed gives you the acceleration and so on, right? So you get the acceleration, you get the centripetal acceleration and centripetal force, nice and easy. Or if you used what I would refer to as the silly equations, the more complicated they need to be, right? But same stuff, same answers. The vertical uniform circular motion stuff, tension of string, we've done enough of these at this point in the videos. I'm just going to leave this in here for you to look at from the file itself, or pause from the video. All the different positions and the direction systems and the angles and so on. So let's to the main event. This one's going too slow apparently, so I end up with a tension force up from a at the top of the travel. So it must not be a string; it must be a rigid post in order for that to happen, and so on. All right. So the physics behind the amusement park ride, the Gravitron, not to be confused with the graviton, which is the exchange particle for the gravitational force, if that particle exists. And so the Gravitron itself, let's load up the video there for that. I think I have it muted right now so you don't have to hear the amusement park noises, but the ride, it's level right now. You walk in, you're standing on the ground here, you're leaning against the side. This guy, is kind of ready for it to happen, so he's pulling himself up. But really what happens is you feel yourself standing on the ground, and then it starts to spin fast enough that you're pinned to the wall. They were standing here, they wouldn't have been able to do that when it was stationary, and in fact they can't stay doing that. If the thing stops, they literally just fall to the ground, right? So that's the Gravitron ride. And then dude here's riding the Gravitron like a boss. One of my earliest meme experiences. Anyways, so that is the Gravitron and so on. Question is, if the Gravitron causes riders to travel in uniform circular motion with a radius of 3.5 meters, and the riders are leaning up against a flat vertical wall. That one is a little bit of an angle, so that would complicate things a bit. Not terribly, but just for the point of making it as a first example here, we'll have a flat vertical wall straight up and down, and we have a coefficient of friction between the riders and the wall of 0.4. Question is, what speed does the Gravitron need to get to so that they don't slide down when the floor drops out? So as usual, you might sort of start with a diagram that helps sort of visualize things here. So we got our horizontal uniform circular motion. And we've got a free body diagram at the side here. We've got a gravity force on the person. That needs to be balanced so that you don't fall down, right? We need the acceleration in the y direction to be 0, right? To not fall down. So in other words, we need to have a force of friction here that is going to completely balance that, right? So we need this right here, the F friction force needs to balance the gravity force essentially, right? So you could say it's equal to the negative Fg, or we could just componentize it, right? Sorry, absolute value it, just look at sizes, right? So let's do that. We have the size of the friction force has to be the same as the size of the gravity force. And so we can get some numbers here, right? Well, that friction force we know is mu Fn, right? So another vector that I should have drawn in the original case here would have been that there has to be an FC, there has to be a normal force, right? So that normal force, in fact, has to equal that centripetal force, right? And the directions are obvious in the diagram, so I could put vector signs and so on. I don't need to, though, here. So I've got mu Fn equals mg. And so I've got my point for Fc because Fn is Fc. It's the only force in that direction. So it has to be providing the centripetal force. And so we've got the Fc, we've got the mg still. Fc, we know, is mv squared over r, right? So something nice happens here where you notice that you can divide out the masses. They didn't give the mass of the rider, and and the nice thing is to see that that doesn't matter, right? So this ride doesn't have to be engineered for a certain mass. Like, oh, you weigh 150 pounds. Okay, you have to go on that Gravitron ride. It doesn't exist, right? They just any mass works. So when you put on there, mass doesn't matter. So when we look at the speed, we're just going to do the work here, right? We're going to divide out I guess I could have put that radius into at that point. So I guess I'll do another line, but we're going to divide out that 0.4 while we're at it. So now I've got v squared over, and the radius was 3.5. And we have over here the g over 0.4. And we end up with what? Here's the result. We have multiply both sides by the 3.5. And v squared equals all of that stuff multiplied out. V squared equals 85.75. Just calculate the numbers. And square root of both sides. And technically plus or minus, of course, always a math person should notice and say and so on. But here we're just looking for a speed, right? So plus or minus directional doesn't matter. It's just a value. And so 9.2601 ... So therefore, if we're going two significant digits, it'd be 9.3 meters per second. Is the speed that it needs to have, the uniform circular motion speed that it needs to have. So that is that. Gave that as a challenge question in past tests or past courses, I should say, and it was a bit challenging. I was surprised people didn't sort of recognize, you have to have the friction balance the gravity. It's the main thing. And then where's that friction coming from? It's coming from the normal force that's there because of the circular motion and so on. Hope that makes sense. The wall of death. Let's go back here. Gravitron, and I'll just find where this is opening. I'll just show you some weird examples of this. Wall of death. You could picture the physics in the world around you, though, right? If you're ever in India on a trip and you see this craziness going on, they got a bunch of motorcycles that are going around and around, right? And you can picture the horizontal, circular motion they're in. And then to add, that wasn't exciting enough. So then they get cars going in the works too, and you get people in motorcycles and people in cars. And I don't know if you've thought about that, but that would hurt, if you're on the motorcycle. Anyways, so that's the scary uniform circular motion example. And then or actually the wall of death, right? The scary one actually is normal Gravitron ride, but scary. So this one, I have a note there. It says, watch the surroundings in the background. You can see it goes like it tilts, right? So in this one here, you're starting out, you're horizontal and so on. And then as the ride goes on, you can kind of see in the background at some point here, it's going to be like trees, ground, and then sky, and then ground, and then sky, and so on. So it ends up tilting at a pretty good angle. The videos from a little while ago. There you go, sky, ground, sky, ground. So it's a nice reference frame video too, right? If I had a video of this from the side, you'd see the Earth reference frame, and that you're in that non-inertial reference frame, and so the kid with the googly eyes there would be, very much experiencing a centrifugal force, right? All right. On to the next thing, the old loop. So if you didn't know what I meant by this, you have the track where you go, through a loop like that. So my first video here, we got Bob Burnquist doing the loop. So Bob Burnquist does the loop. And so this guy is on a skateboard, and he grinds a couple rails first. There we go. But the main event here was this guy down here, right? Coming in, trying to do the little loop-de-loop, wipes out, eats it hard, a couple times, worth a replay, I guess, of that one, and then managed to do it, and the crowd goes wild, and all that stuff, right? You can picture being at a fun event like that, and then you'd be thinking about the physics of this situation and cursing Mr. Horn, or thinking, you never know, if you're like, cool, I can analyze the actual forces involved and picture it. You could calculate the speed necessary that you need to go into that thing and predict in advance whether it's going to be successful or not, right? And that's exactly what they did in this video. I have to be really careful not to have a whatever you call it, copyright infringement thing going on here. So I'm going to try and just show very specific time intervals, and hopefully I get away with it. So in this guy here, we're going to do 5th year loop to loop. And let me just pause that right away. So it gets loaded up. Poor computer, a moment here. All right, so from the 10-second mark or so, that should be good enough.
These Hot Wheels loop the loop. Come on, Tom, send one down. Here we go. Yes, but what we wanted to know is, could you do that in a real life family size car?
Yeah. Okay, so that's the idea. Can you do that in a family car? All right, so fast forward ahead here, you can see like the apparatus they built, big track thing. And this section here actually is kind of funny. They're like, they're doing the math. They're like trying to figure out what speed you'd have to go. And this is the stunt driver, and he's like, okay, well, I guess having seen the math, it makes me more confident, but still not sure that's going to help me calm down when I'm pressing on the gas pedal. And he's done this sort of thing in airplanes, so there he's going loop to loops in airplanes and so on. But to do it while driving is kind of a trick, right? You have to follow that white line, keep that in the center, and you're angling a bit to the side as you go, or else you're gonna like go off the track. Now they have guardrails on it, and they've got a little vehicle that has like a really good roll cage all welded into it and that. So the guy's gonna be safe, but bruised up a bit maybe, right? So here's him going in with the speed having been calculated and so on. They calculated out that it would be at 18 meter per second speed that you need to go in. And what we're going to do is we're going to do the physics of it and see if we agree. And so they didn't really show the whiteboards enough for me to be able to like do much from that. So at one point, when I originally did this, I saw this video, and we just went through this as a class together. It was kind of a cool, sure, put our heads together and think about what we'd have to consider for trying to do this in a real life situation. Is air resistance something we have to consider? Is all these things. So the one thing that I'll go through in the work here is the air resistance and friction. You kind of have to just say, okay, well, let's just go a little faster to compensate for those, right? But the biggest one would be, think about how hard it would be to get a car up that high, right? And so it's going to come in with kinetic energy, and that kinetic energy is going to convert to gravitational, and that's why you slow down so much, right? And I'm guessing this car probably doesn't have a ton of horsepower. It's probably not able to mash the throttle and get through. Like he's really probably just trying to go with a constant speed, and so really the car is going to slow down as he goes here, unless he, as part of this steering process and going through this, is going to get on the accelerator as he goes. So I think they probably decide it easiest just to go in with a constant speed and just let gravity and physics do the work, right? So back to the video here. We're looking for the 244 mark. Yeah, here we go. This is him going in.
Our speedo with GPS, 36, 37, and then checked again with a calibrated radar.
So I think they're doing like miles per hour there. So you'd have to do the conversion from, meters per second.
Miles an hour can be calculated as the ideal entry speed. Slower than this, and he'd fall.
Right, that would be pretty bad for the car and for the track system if he went too slow. Any faster, of course, you'd have way too big of forces on him and on the track. right? It'd be
But knock
bad.
him unconscious,
And
and
so
exert a dangerous force on the ground
that
structure.
is that. And then we jump ahead to 325 for when he actually does the trick. Here we go. Pretty cool, right? So here's the analysis, right? Note if we thought of like what the minimum speed would be, then you just want the gravity force equal to the centripetal, and you could calculate out what speed that would be, right? That's probably not what you'd want to do though, because then you'd be like, there'd be no contact force between the car and the road. It'd be pretty slippery steering at that point, right? So you want some friction to kind of at least stay kind of like normal, is what I decided. When we did this, we said, okay, we'll probably want the normal force at the top to be at least as much as it normally would be on the ground, right? Which means you're going to have a way bigger normal force here, right? That's the trade-off, right? And forces on the system, they have it all braced, you can see, right? But you probably want the top to stay normal at least, or some fraction of that. Maybe you'd be okay with like 60% or something, but let's just go with the same for now. Okay. And so the analysis would be, your net force is equal to your gravity force plus your normal force. Your net force, of course, is your centripetal force. So you can just work this out, right? You got your mass, your gravity, your gravity, and you have your normal force equal to the gravity. So it kind of ends up being like two of the gravity, right? So you can see here that they wouldn't really have had to, if you go through the video and watch it from the link, you don't have to factor in the mass of the car, which is kind of neat, right? The mass of the car matters for like how strong the track needs to be, but it doesn't matter for the speed. So that's something to know. And so acceleration equals centripetal acceleration is 2 g's apparently in this case, which is 19.6 meters per second squared. Notice, it was supposed to be 18 meters per second. That's not this number, right? That's the acceleration at this point, right? So we still have to get the speed. So let's do that. We know acceleration equals v squared over r. And so boom, 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 we do our work and we get our speed, right? So we have 10.9 was what I got at first. And I was like, man, that's not very close to 18, but something to consider here, right? This assumes uniform circular motion. When the car is going up the ramp, it's going to be slowing down a lot, right? So we're going to have to come in with some extra speed so that we end up with that minimum, right? So we're going to simplify this. We're going to be letting the car coast through the ramp. We're not talking about factoring in engine contributions to the energy. So this goes back to some grade 11 stuff where we have kinetic energy has to equal the gravitational potential energy at the top, right? We've got the transfer from one to the other. So we want enough speed left to have this 10.9 meter per second, I suppose, at the top, right? So yeah, there's your change in your kinetic energies. Notice mass is canceling out again. And we get that change in height, the diameter of the ramp, and the math works out to give us about 18.9, right? That's what we have to come in with. So that's for coasting. So maybe the car's going to add some energy. So maybe that reduces the speed a little bit. If you're thinking, okay, I'm going to keep on the gas, so maybe you reduce that to about the 18, right? We're certainly in the ballpark of what they must have calculated out. So the video also says, if you watch it, that he's going to experience 6 G's, right? 6 gravity force accelerations, which is our acceleration is 53.14. Divide that by 9.8, you get 5.4 G's, not far off at all. And then you think about, okay, well, where are you going to feel the most acceleration due to the ramp pushing on you? That'd be at the bottom, at this section here, right? And so if we go in that kind of section, we just simplify it by looking at the bottom, then you'd have your normal force and your gravity force you could analyze, but we don't have the forces because we don't even need a mass. So instead we can just look at the gravities. That's something new you're going to see in the homework as well. That you can just work on gravity the same way you'd work with force. So if you look at the centripetal acceleration, and you have your G, and you have your have your acceleration from the applied force. This part is here, right? So you have your gravity, and you have your applied force from the ramp making you accelerate, and you have your what the centripetal needs to be. You add that up, you get like 6.4. So, it feels like we're all over it in terms of the analysis, right? So kind of neat. So watch the video. Hopefully, I can leave this one posted on YouTube. If not, this will just be posted within the D2L site if they are upset about me using that video. And yeah, that's all for now. These are very much just review stuff, like normal questions you've seen. Okay, and then the loop, and the gravitron in there as an extra. And you've got this angle of the beads thing, which is review from a previous lesson as well. So, as always, thanks for watching, and I'll see you next time.